thank you. Okay, so here we have the answers to the sheets. So what I did is some of these are going to need pictures to explain. So I'm going to actually just bring over the document I made to show you these. Okay, so first we have water. And so if you're not familiar with chemistry or it's been a while, so water looks like this, H2O, and it participates in hydrogen bonding. So it's between the O and the H. So you look at those positive and negative charges on there. So the negative charge of the oxygen is attracted to the positive charge of the hydrogen. And when we're ranking polarity, if you didn't know that water is highly polar, something that's highly polar is going to have different electronegativities or very different electronegativities. Okay, so that's, I wasn't planning to go so into the inorganic stuff because I don't know if you're going to be needing that in your lecture. So if you are interested in getting a little bit of a refresher about electronegativities and polarities in the periodic table, I put a bunch of my lectures from inorganic chemistry on the 2U page, and I wrote which pages on those lectures would have information about polarity or electronegativity or bonding. So I don't want to go too far into it. So if you do need a refresher, just check 2U, and then you could always email me if you had questions. So that's our water. And then we have ethanol here, which has the same, it's basically the same explanation as water. This is our ethanol molecules, and you'll notice that the positive charge on the hydrogen is attracted to the negative charge on the oxygen. Okay, and that's going to be highly polar as well because of the difference in those electronegativities of oxygen and hydrogen. Okay, so dichloromethane, do I have a picture of it? Yeah, I do. So dichloromethane looks like this. It's just a carbon that's 2 chlorine and 2 hydrogen are bonded to it. So those are going to have very different electronegativities, the chlorine and the carbon. And it's going to be something called a dipole, or just a dipole intermolecular force there. And so this is just a little bit of an explanation. So that occurs when there's the negative charge of something and the positive charge of something are together. So in this case of dichloromethane, it's going to be that carbon and then the chlorine. Okay, and it's going to be slightly polar. This was in the worksheet, so hopefully you saw this picture. And if you don't remember anything about net dipoles, that's also in those lecture notes that I put on 2U. So if you wanted to refresh yourself, but I don't know if you need that for organic chemistry, but if you wanted to get the explanation. So basically those pictures would tell you that the bonds do not cancel out because they're not symmetrical. So if you're looking at it from this angle as a tetrahedron, the chlorine might cancel out if it was drawn like this, but if you built this, you would notice that the chlorines go in opposite directions and they can't cancel each other out. So hopefully the chart up above this helped with that, but if not, then this picture would have helped with the dichloromethane being slightly polar. Okay. Any questions so far? Is this helpful here? I made this like an hour ago, so I hope it's helping you guys. Sure.
Oh, I'm sorry. I was just gonna ask, is there any way you can put this onto you so that we can?
Oh, yeah, definitely. I'll put this, I'll neaten it up a little bit. It's kind of messy. So yeah, I'll definitely put this onto you.
Thank you so much.
You're welcome. So we have perfluorooctane, which looks like this. So you would use the chart that's up above there. Let's see. It's going to be another one of those dipole moments that I described here, where you have the electronegativities of the carbon and the fluorine. They're the electronegativities are very different. And so that's going to be the dipole is going to be the intermolecular force. And then do they cancel each other out? So this one is going to look like this. It's basically drawn and represented in the same shape. So this is symmetrical. So unlike the dichloromethane, the perfluorooctane, those can cancel each other out, and so it's symmetric. So hopefully the chart above helped you determine that this would be symmetric, and so this is going to be nonpolar and dipole. Okay. Next, we have hexane. So hydrocarbon chains like hexane or pentane, those alkanes that you've been going over in lecture, they're all governed by the weakest intermolecular force there is, which is this London force here. It's basically like a temporary hold that's placed on the molecule. So hydrocarbon chains are governed by that really weak force. And hydrocarbon chains, if it's just all carbons and hydrogens mostly, it's going to be a nonpolar molecule. So you wouldn't expect something that's nonpolar like hexane to ever dissolve into water. So anything with that long carbon hydrogen chain is going to make it nonpolar. Methylene blue is going to be ionic. So what I was describing with that positive and negative charge, I'm actually going to just show you the shape of it here. So the methylene blue has those positive and negative charges on it. So if you look at the structure of it, you can see that it has the positive and negative there. So that's how we would determine that it's going to be ionic. It's going to have those charges on it. It's charged.
Where is the chlorine bonded on that? I was kind of lost.
So I'm actually not sure. Methylene blue is a dye, so I don't know like if it's, I can't remember if it's powdered or liquid, but I think it's just there in whatever state methylene blue is, the chlorine is there. I'm actually not 100%.
It's a liquid. We use it in the
liquid?
OR.
Oh, okay. So I would guess if it's a liquid, the chlorine is just floating there in solution with the, that would be my guess. I'm not entirely sure. Okay, and then anything that, so the chart that's up above here, so an ionic, something that's ionic is going to be highly polar. Disperse red was another one I was not 100% sure on. So my guess with disperse red here and what I could find, it's also one of those dyes, is it's dipole because a dipole intermolecular force has bonds of those different electronegativities that we talked about with dichloromethane and perfluorooctane. So my guess was that because there's carbons and oxygens bonded together and carbons and nitrogens bonded together, that's what makes it dipole. I couldn't 100% figure that out, but that's my guess. I would never like test you on that or anything. It's just I just like to look at the shapes and see. So also for the dipoles, they don't cancel each other out. So it's not like perfluorooctane where anything can cancel out. So that's why the dispersed red is going to be slightly polar, because up in that chart, there's I think it's the last one, step 3. If the molecular geometry of the molecule can't cancel it out, it's slightly polar. Okay. Vitamin B1 is going to be another ionic one. And vitamin B1 is right here. So you can see that it has that negative and positive charge there. I forgot to look this up. Someone asked me this a few hours ago about this HCl hydrochloric acid in there. I'm not sure. I think B1 is riboflavin, or I can't remember what B1 is. Thymine, I don't know, but I'm not really sure what the hydrochloric acid does there. Maybe it stabilizes it. I'm not entirely sure, but this is what really we're focused on, is this ionic nature here. Okay, and then something that's ionic is going to be highly polar. And then we have vitamin B2. So vitamin B2 has a lot of these hydroxyl groups. I don't know if you've gone over hydroxyl groups with Professor Levy, but they're OH groups basically. So I did make another sheet. This is up on 2U. And if you're interested in just learning a little bit more about vitamins and the functional groups on them, this is up on 2U, and I wrote more in depth about the polarity and their behavior in water. I'll bring that up when we go to vitamin C, but this is also on 2U if you wanted to just get a little bit more information. So basically what vitamin B2 can do is it can form hydrogen bonds with these hydroxyl groups here. So if this is in water, it's able to form those hydrogen bonds with water. Okay, so the dominant for intermolecular force is the hydrogen bonding because of those hydroxyl groups, and then it's going to be highly polar. Something that's hydrogen bonding is also highly polar. And then we have vitamin B6. It's basically the same explanation. It's again those hydroxyl groups here, the OHs. Those can undergo hydrogen bonding as well. And highly polar, there's more oxygens. Oh, this is another thing I left out. So more oxygens and nitrogens was one of those steps up above. I think there was a question and it said, are there 5 or less carbons per oxygen and nitrogen? So for this one, there's a lot more nitrogens and oxygens to carbons. So that's how we know it's highly polar too. But besides that, something that's going to be able to hydrogen bond can be highly polar too. That's another way to explain it. And then vitamin C. So vitamin C, where did my document go? Vitamin C is going to do hydrogen bonding and highly polar. And that's one that I wrote in this document here. So vitamin C or ascorbic acid, I found this picture where the hydroxyl groups are actually circled here. And then this is what it looks like when vitamin C is hydrogen bonding. So when it's hydrogen bonding, see those hydroxyl groups are hydrogen bonding to these water molecules there. So they are hydrogen bonding. That's the dominant intermolecular force. And then there are more oxygens and nitrogens to carbons, and also they're hydrogen bonding. So this is going to be highly polar. Okay, and then last but not least, we have our vitamin E. So vitamin E, did I do vitamin? Oh no, so I wrote about vitamin D here, but it's basically the same premise. So basically vitamin E is a fat soluble vitamin. So fat soluble vitamins or fatty molecules have this long hydrocarbon chain here. And they're going to make the whole structure non-polar because this basically outweighs this single hydroxyl group here and this oxygen here. So that whole hydrocarbon chain just trumps the hydroxyl group here. Okay, so fatty molecules are going to be non-polar, so their charge is evenly distributed. And like I said, with the hexane up here, those hydrocarbons are going to be they're going to be governed by the weakest intermolecular force that there is, the London forces. And then so I put in the sheet that's up on 2U just a picture of vitamin D, which is another fat soluble vitamin, and you can see how many carbons there are, and there's just that one hydroxyl functional group there. And then I also wrote about what happens in water, and so that'll help you with the lab if you choose to write about the olive oil in the water. So basically, the vitamin E is going to be non-polar, and because of that hydrocarbon chain, and it's going to be governed by the London forces. If you were to put a fat soluble vitamin like vitamin E or vitamin D, vitamin A, it's actually going to repel, or the water is going to repel the olive oil because the water likes to interact with itself. So the water molecules are attracted to each other. And then when they see the fat molecule come in and has this long non-polar chain, it has no interest in it. That's why if in the video, you'll see that the olive oil just floats off at the top. and is separate from the water because the water is basically repelling it. Okay, so those are the those. So then just these 3 questions here. If we're putting something like methylene blue, which is ionic and highly polar, in water, which is also highly polar, like dissolves like. So something that's highly polar is going to be soluble and something that is also highly polar. So that's going to be soluble. Oops. Let me drag this down. And then dispersed red is going to be slightly polar. So water being highly polar is, if we had to pick like a yes or no answer, we're not like, we don't want to be 50-50. If just we want to know yes or no, is it going to be insoluble, then it is going to be insoluble because dispersed red is slightly polar and water is highly polar. Maybe if we dumped the excess amounts of one or the other into each other, they would dissolve, but we don't know for sure. So we're just going to say insoluble. Ethanol is highly polar. So because methylene blue is also highly polar, it's going to dissolve in it. The methylene blue will dissolve in the ethanol and it's going to be soluble. Dispersed red, the same explanation. So we don't know with 100% certainty, like the amount, the temperature, any of those other factors. So just knowing that dispersed red is slightly polar and ethanol is highly polar, we're just going to say it's probably just going to be insoluble unless you change X, Y, and Z. And then dichloromethane, which is slightly polar. If we combine it with methylene blue, which is highly polar, we don't know for 100% certainty. So we're just going to say yes or no, soluble, insoluble. It's going to be insoluble. But with dispersed red, dichloromethane is also slightly polar and dispersed red is slightly polar. So we definitely have 100% certainty that something slightly polar is going to match up with something else that's slightly polar and be soluble. So that's how you would solve that section there. Okay. Does anyone have any questions about those? Okay, so hopefully knowing some of this information about hydrogen bonding and polarity, that's going to help you with the lab that you're going to be doing. So in the lab here, you have these vitamins. And so with water and hexane, with this, given this information up above, hopefully you can see, oh, hydroxyl groups here, long hydrocarbon chain here. Is it going to dissolve in something polar or non-polar? Okay, and then the second part is just the experiment. So does anyone have any questions so far? Okay. So now that we're done with the breakout room activity, I can put you back into breakout rooms and you can either watch the video, do the experiment on your